environment here, and I enjoy mathematics and the city and the weather, so thank you very much. I will speak about joint work with my former student, Peng Shui Shi, who is very talented, and this is about some generalization of index theory, and there will be some topology in this lecture, but there will be also some analysis, so I understand that it's a little bit not in the area of many people in the audience, so I'll try to be elementary and sort of give a colloquial type talk. So I apologize before the experts, so it will be pretty elementary in the beginning at least. So this is the plan. I will recall the Atiyah-Singer index theory, I will recall what the index is and so on. Then I talk about generalization of Atiyah-Singer index theory, which is called Atiyah-Patodi-Singer index theory, and Atiyah-Patodi-Singer. Atiyah-Singer index theorem is in closed manifold, and Atiyah-Patodi-Singer on manifolds with boundary. And then I'll start talking about manifolds, non-compact manifolds, and non-compact manifolds without boundary. There is a classical by now theory which is called Khalil's index theory, which I also will recall, and then I'll start talking about our generalization of it, and we'll talk about generalization of this Atiyah-Patodi-Singer index theory to manifolds with non-compact boundary, and as a part of it and consequence of it, I will discuss something which we call relative eta invariant. We'll come to it. So that's the plan. Okay, so let me start, and so I start with the first part of the plan, Atiyah-Singer index theorem. I consider compact closed manifold. And I will consider two bundles of it, two vector bundles, which I will call E plus and E minus, and just two vector bundles, but I think about them as about one vector bundle, which is a direct sum of those two, and I will call it graded vector bundle. So a graded vector bundle is just two bundles, basically. And now we consider an operator D, which is differential operator between sections of this. So I will denote it with, say, smooth sections of E plus to smooth sections of E minus. And so maybe it's better to denote it D plus. That will be the operator, and I assume that this operator is elliptic. So it's a differential operator. For most, it's not important yet, but for most part of the talk, it will be first order elliptic operator. And that just means that it's leading symbol, which so let me write in coordinates. D can be written as sum of Aij of x. Let me write it first order. Plus. So this collection of this AIs, those are matrices which, the collection of those matrices form a leading symbol, and I assume that this leading symbol is invertible, so this is elliptic operator. And the basic theorem of the theory of elliptic operator says that if D is elliptic, and recall that our manifold is compact, then in this case, it is Fredholm. What does it mean, Fredholm? That means that its kernel and its co-kernel, which is just the range, let's say, of two sections of E minus, quotient by the image of D, are finite dimensional. So if both kernel and co-kernel are finite dimensional, that means that the operator is Fredholm. And the theory of elliptic operator says that if operator is elliptic, it's Fredholm. And so there's some confusion, which I'm always confused about my notation, so I wrote here D plus, and what I often do, I consider the adjoint operator, which acts in the opposite direction, so it will be D minus, which is D plus adjoint. And I will form a matrix D minus D plus, which acts on sections of the total bundle of E. And sometimes we will talk, sometimes it will be convenient to talk about the whole operator D. Okay, for Fredholm operators, there is something which is called the index of a Fredholm operator, and the index is defined as the dimension of the kernel minus dimension of the co-kernel. Oh, let me write D plus probably here. Or equivalently, it could be written as the dimension of the kernel of D plus minus dimension of the kernel of D minus. So that's the index. It's kind of an interesting notion. It was introduced by Fritz Noether in the 20s of the last century. Fritz Noether was a very interesting personality. He was somehow he's not known enough because he's sort of in the shadow of his great relatives. He was the son of Max Noether from Material Rings and the brother of Emmy Noether. And somehow there is a proof that he was not as smart as Emmy Noether, because when Nazis, he of course was from a Jewish family, and when Nazis came to power in Germany, they had to run away. And Emmy Noether famously ran to the United States, but Fritz Noether ran in the opposite direction. And he actually worked for a couple of years in Siberia. And then he was arrested and died in a Russian concentration camp. But he was a very fine analyst, and in particular he introduced this notion of index. And what is it good for? Why is it interesting? So the main observation is that it's extremely stable. So, for example, if you add the operator of lower order to D, or he did it in more abstract settings, so if you add a compact operator to D, then the index does not change. If you just deform D continuously inside the space of compact operators, or of Fredholm operators, then the index does not change. So here you can set topology conference. That's you already feel something topological in it. It's stable under deformations. So if you consider the kernel of D, the dimension of the kernel of D, then of course when you deform a matrix, then the kernel might jump. So some eigenvalues could cross 0 and the kernel will jump. The same could happen to co-kernel. But the observation of Fritz Noether was that they do it simultaneously and the index is stable. So it's a nice topological thing. And so if you think about elliptic operators, what follows from it, first of all, this B, which I wrote there, is irrelevant. You can change it. And it's depend only on A, which if you do it invariantly, then what we call the leading symbol of this D will be a function on the cotangent bundle of M. So maybe let me write it like this. It will be a section of the cotangent bundle of M, of the endomorphisms of this bundle. So it will matrix valued function on the cotangent bundle. And this matrix valued function should be invertible outside of the zero section if the operator is elliptic. So now we say that it depends only on the leading symbol. The index depends only on the leading symbol. And not only it depends on the leading symbol, it depends upon the equivalence class of leading symbols, upon homotopy equivalence class of leading symbol. It doesn't change the homotopy. And so naturally there is something topological in it. And it was Israel Gelfand who posed the problem. I think it was in around 60. He posed the problem of computing this index topologically. And before I come to it, sort of, let me just say why is it important? Why index is interesting? Why do we need index? So what's good in it? So we said that index is stable. So very often we're interested just in the kernel of D, because what's kernel of D? It's the space kernel of D is the space of solutions of this homogeneous differential equation. So if you are analysis, you are very interested in how many do you have solutions. So how many solutions do you have for this equation? And it's, of course, extremely difficult, notoriously difficult problem, unless the operator is very simple. So suppose you could deform your operator D to a simpler one. For example, you remove the potential, remove B. The operator will be simpler. And you prove, then you can compute, then sometimes, if you are lucky, you can compute the kernel. You compute the kernel, you see that, and you compute the kernel of D minus, so you can compute the index. If the index is positive, that means the kernel must be non-empty. It has positive dimension. If the, at least as dimension of the kernel is at least as big as the dimension of the index. So if the simple operator has solutions, not only has solution but has non-trivial index, positive index, then deform operator also has solutions. So that's the nature. You can use this basically topology to evaluate, to at least estimate the number of solutions of a differential equation. And that was the question of Gitler. He said, find this topological method of computing it. So compute it. And Atiyah and Singer are famous exactly for this. 3 years later, they solved this problem. They gave a formula, and there are many different forms of their formula, but let me give you one of them, also not with all the details. So they computed the index of D of this operator, and the computation gives you evaluation of some cohomology class over M. Let me do even more. There is something which I call AZ. It's Atiyah-Singer integrand. That's some explicit closed differential form. So it's closed differential form, it represents some cohomology class, but that gives you even a little bit more. That's something which I'm writing now is something which is called local Atiyah-Singer index theorem. But the point is explicit differential form, which depends only on the symbol of D and the geometry. So you have to fix some metrics and geometry. So you fix something like metric on M, metric on E plus and E minus, scalar product on E plus and E minus, and combining them, you can construct an explicitly given canonical differential form. And the cohomology class which it represents is exactly the index. And that's the essence of Atiyah-Singer index theorem. And again, that means that now, and that's how Atiyah-Singer index theorem very often used, we can use topology, evaluation of this cohomology class, to prove that some differential equation has solutions, or even estimate the dimension of the space of the solution, to give the low bound for dimension of the space of the solutions. Let me mention something which is called hit kernel proof of Atiyah-Singer index theorem. So there is an analytical approach to original proof was different, but there is an analytical approach to the proof of Atiyah-Singer index theorem, and let me very, very briefly mention it. And what you do, you consider the operator D minus D plus, and you multiply it by T, and you consider the exponent of it. So this thing is called hit operator. This hit operator is describes actually if this D plus will, for some examples will be just Laplacian, then it describes the propagation of heat. And the point is that sort of what this is a self-adjoint operator. It has eigenvalues, so eigenvalues of this will look like e to the negative t lambda. And so they tend to zero, eigenvalues of this operator, of differential operators tend to infinity. This will tend to zero, and it will tend to zero pretty fast. So the point is that this is trace class operator. So even though it's not a matrix, but infinite operator acting on infinite dimensional space, its trace is well defined. Some of its eigenvalues converges. So you can consider the trace of this operator, and you can consider also the trace of the similar operator when you replace switch d plus and d minus. And if you consider those two operators, d minus, d plus, and d plus, d minus, they're very similar. And in fact, it's very easy to see that they have basically the same spectrum, the same eigenvalues. And the multiplicities of those eigenvalues also the same, except at 0, except at the kernel. And the kernel of this operator is the kernel of d plus, and the kernel of this operator is the kernel of d minus. And so if you combine this together, then you get something which is called Maxim-Braverman formula. But this observation is due to Maxim-Braverman, but if you know this, this is an easy exercise for an undergraduate student in functional analysis, that if you take the difference of those traces, then it's exactly equal to the index. So the index is equal to the difference of those two traces. Now, notice something strange. Here, the formula depends on t. And this trace depends on t, and this trace depends on t. But this doesn't depend on t. So that means that the difference also doesn't depend on t. And now there is some analytic approach which I won't bother you with, but you can do so this function as a function of t. If you consider this as a function of t, it has nice asymptotic expansion, and the coefficients of this asymptotic expansion could be computed by local formulas. So you have So you have an asymptotic expansion of this expression, and you know that this all local coefficients, all these coefficients of the asymptotic expression must vanish because except the free one, except the one which doesn't depend on t, because the result doesn't depend on t. So there is only basically this is expressed in terms of this coefficient of the asymptotic expansion, free coefficient in the asymptotic expansion of this, and free coefficient of asymptotic expansion of this, which could be in principle computed. Again, I apologize, I'm extremely brief here. If I want to use it later, so if you're lost here, just forget about this. But the point is that you can get a local formula just from this Maxim-Braverman formula. The problem is that this local formula is extremely difficult, because it's a long, complicated formula for this coefficient here, a long, complicated formula for coefficient here, and then you take the difference, and the difference is something, and the difference turns out to be simple. It gives you Atiyah-Patodi-Singer integral. And you have to see why is it. It's something which Patodi called, who was the first to use this approach, called fantastic cancellation. In this long, complicated formulas, there is a fantastic cancellation, lots of things cancel out, and you get a simple formula. And then after Patodi did it in the beginning of 70s, lots of people improved it, and probably the best approach is due to Ezra Gitler, who gave sort of a proof which could be explained in a couple of hours of Atiyah-Singer index theorem, of local Atiyah-Singer index theorem using this approach. So that's what I wanted to say about Atiyah-Singer index theorem. So again, the point is that we're interested in the index of this operator, because basically we want to know the space of solutions, but that's notoriously difficult. We want the index, and the index is given by topological formula, given by Atiyah-Singer. In this form, which I am interested in, is given by the integral of some explicit differential form, and this differential form could be found out of hit kernel analysis. Not easy, but could be done. Okay, today I am interested in some generalization of it, and the first generalization is due to Atiyah-Patodi-Singer. So it's 5. And so what they did, they considered a manifold with boundary, which I will draw like this. So it's compact manifold with boundary. So it's M. There's the boundary of M. And sort of one of the assumptions, which here is not really necessary but makes things much easier, they assume the product structure. So that's why I drew it as a cylinder, because they assume product near the boundary, which means that my operator could be written in the form, so this is t coordinate. It will be ddt plus some operator on the boundary. So A is the operator acting on the boundary. And it's, so it's differentiation along the boundary, and the assumption is that, so this sort of fibers like this, and on each fiber it's exactly the same in a small neighborhood of the boundary. That was the assumption. And now they consider this operator and want to discuss the index of this operator. Now, here there is a problem. And the problem is that if I consider this operator, it's certainly not Fredholm. If you consider an operator on non-compact manifold, just think about differentiation on half line. Then the kernel is infinite dimensional. And the solution is well known, you need boundary condition. Now, let me also assume that operator D is what is called Dirac type. And sort of, I do it for pedantic reasons, otherwise I had to change many of the statements. If you don't know what it is, so that basically means that D squared looks like Laplacian, or leading symbol of it is like Laplacian. But you can also ignore it. In fact, everything could be generalized to first order operators. Just let me just say it in order to be accurate. So now consider this operator. So what's the boundary? So the solution, how to make the problem Fredholm, how to cook up Fredholm operator out of operator on manifold with boundary is boundary conditions. So we know that every physicist knows that if you have Schrödinger operator, say on manifold with boundary, on some domain with boundary, then you need boundary conditions to set up the problem. So you need boundary conditions. And usually people consider sort of for Laplacian, people used to the Dirichlet boundary condition, the function, restriction of the function to the boundary is 0, or Neumann boundary condition, the normal derivative is 0. Those are nice physical boundary conditions, but unfortunately, they don't even always exist for a Dirac operator. When you consider operator of first order, sometimes there are no nice, I mean, you can always, let me take it back, you can always put boundary condition, but there is something which is called elliptic boundary condition. It's a little bit more than that, but basically for our purposes, there's boundary condition which produce Fredholm operator. There are some conditions which is called elliptic boundary condition, some nice boundary conditions which produce elliptic operators, and they don't always exist on, for first order operators. And as Atiyah-Patodi-Singer write in their paper, this problem holds the progress in this for several years. And then they introduced a new boundary condition, which they call Atiyah-Patodi-Singer, which now are called Atiyah-Patodi-Singer boundary conditions. Or sometimes called global boundary conditions. Global boundary conditions. So what are global boundary conditions? So global boundary conditions are constructed in the following way. So this operator A is the elliptic operator on the boundary of M. And as elliptic operator, it's also Fredholm, not only Fredholm, it has boundary of M is just compact manifold with boundary, it has discrete spectrum. So it just has eigenvalues. And its eigenvalues, it's first order operator, so think about again operator like I ddt on a circle, or dd theta on a circle. Consider this operator. Then the eigenvalues will be, eigenfunctions will be just I to the tn, theta n. And so when you differentiate it, it will give you n. So that's the typical station. The spectrum is like integers. So there are infinitely many negative eigenvalues and infinitely many positive eigenvalues. So the spectrum of A look like this. There is 0, and there are some points here, and some points here, and there are infinitely many of them. So you can consider just part of them, say negative ones, and consider all the eigenfunctions corresponding to them. So your L2 space of the boundary will be the sum, direct sum, of what we call L2 smaller than 0 and L2 bigger or equal than 0. So here I take the span of all the eigenfunctions with eigenvalue smaller than 0. Here the span of all the eigenfunctions with eigenvalue bigger or equal to 0. So as an example, let's consider this case again. A is I d d theta on S1. So let's draw this S1. So this L2 smaller than 0 will be span of e to the negative I theta n and bigger than 0, and bigger than 0 integer. So of course those things are like z to the negative n. So it's Laurent. So basically what you have here is power series in negative z. So in other words, those the functions which extend holomorphically to the complement of the circle. And the other part, this one, is the function which are powers of z, which extend holomorphically into here. So that's decomposition, what's called Hardy decomposition into space of L2 functions on the circle. The space of L2 functions on the circle decomposes into the space of functions, boundary values of functions which are holomorphic inside, and boundary values of functions which are holomorphic outside. So now the theorem of Atiyah-Patodi-Singer says that if I say that what's boundary values, that means that boundary value problem. That means that I consider only those functions whose restrictions to the boundary satisfy something. So they consider the operator, which we call DAPS, operator from the spaces of sections U, such that U restriction to the boundary is N2, is in L2 smaller than 0, and it is mapped in just usual L2. So that will be the operator. So this is the boundary condition. I consider only functions of this sort, and this operator is Fredholm. So it's a new type of boundary conditions. And for operators of Dirac type, it always exists and always give a Fredholm operator. Okay, so if we have a Fredholm operator, we can ask about the index of this Fredholm operator. Do I still have? So let me let me write again the Atiyah-Singer index theorem for closed manifolds. We have index of D is equal to the integral over M of this thing which I call AZ, Atiyah-Singer integrand, closed differential form which canonically defined by geometry. For manifold with boundary, index of DAPS will be, well, you expect something like this here, so it's still here. But now this is not even an integer, because you integrate closed differential form, but by over half of the manifold, or the manifold with boundary. So there is, you need a correction term. And the correction term, let me first write it and then explain. So that's the correction term. So this thing is just the kernel of A, that's clear. So this is a new invariant which is called Atiyah-Patodi-Singer eta invariant. So let me just write from this to understand what it is, let me just compute it out of here. So eta of A is equal to, well, let me write negative eta of A, is equal to 2 index D minus Atiyah-Singer integral and plus dimension of the kernel. So, in other words, I just say that, well, forget about dimension of the kernel, that's kind of here, but say, think about kernel could be empty, so then that could be 0, then it's not here, so it's not important here. Forget about this. So, we just say that, well, if it was closed manifold, that would be the, this would be the index. So we consider the difference and say that, well, that's the correction, the difference. Well, there is some decoration 2 and negative 1, which of course is just normalization. So basically, this is the correction term. So the first observation of Atiyah-Patodi-Singer is that this correction term, in principle, could depend upon all the data, upon all the big manifold M, operator D, and so on. They say, no, it depends only on the boundary, only on the restriction of the operator to the boundary. So that's the first part of Atiyah-Patodi-Singer's theorem. They say the correction term is a new invariant of the boundary operator. So a theorem of Atiyah-Patodi-Singer says that this eta invariant, first part, eta invariant is an invariant of A, so it depends only on the boundary operator. And the second part they computed. And so before I give you a formula, let me say what it is morally. Morally, it's the number of positive eigenvalues of A minus the number of negative eigenvalues. Well, that's a familiar thing for everyone who took undergraduate linear algebra. That's called the signature of the operator, right? Number of positive eigenvalues minus number of negative eigenvalues. A useful thing. One problem, both numbers are infinite. So both numbers are infinite, so what to do? So we need to regularize. And the way to regularize, to define something which is called eta function, which is just well, one way of defining it is the following. You consider, let me write it in the following form. Lambda to the negative s negative 1 times lambda, sum over lambdas in the spectrum of A. Something is wrong. What's wrong? Oh, of course, it's not lambda here. In this form, let me write it like this. So I just take sine of lambda here. So in other words, I take the sum of all of lambda to the s, of absolute value of lambda to the negative s, for all positive eigenvalues minus the sum for all negative. So it's like the signature of A to the negative s, if you wish. One way of writing it, and that's why I was. So you can also write it. So what's the signature? What's the sign of lambda? It's lambda divided by absolute value of lambda. So you can write it as lambda, and here will be lambda minus s minus 1. So it's a trace actually of the operator A to the negative s negative 1 So the theorem is that this, well, it's not hard to see that this function, this actually power series, is convergent, absolutely convergent for large S, for large real part of S. So somewhere for large S and gives an analytic, gives a holomorphic function. So if you take somewhere here, it's holomorphic. Then you can try to make an analytic continuation of it. And a little bit harder, but not difficult to show, that it has a meromorphic continuation to the whole complex plane. So only poles, it could be extended everywhere, and only poles, and we know where the poles is, and in particular, in principle, it could be in 0. But then a non-trivial part, regular at 0. That's actually the only proof in which exists in general is using this index theorem. So basically, they consider this function, they computed the index using this hit kernels and all the stuff, and they just said that its value at 0 must be this correction term, and so that's why it's regular there. Now, for Dirac operators, actually, there are no other proofs, but they're anyway very complicated. So, the Atiyah-Patodi-Singer theorem says that this, the sort of easy part of it says that there is an invariant of A, which is the correction term, and the harder part computes it. And let me just say, without writing anything, that this formula could be rewritten using Mellin transform in terms of hit kernels. So it's kind of related to hit kernels. Okay. Now, my goal is to extend it to, and that's part of ongoing project. We already have 4 papers about this, or 5 papers about this, and 2 more are being written, and probably will be more, about general extension of the index theory for manifolds with non-compact boundary, different aspects of it. But I want to introduce index on manifolds with non-compact boundary. So now my manifold M is non-compact, but not only M is non-compact, its boundary is non-compact. And so what to do? And I immediately run into several problems. First of all, the operator, even without boundary, will not be Fredholm. So first, even when Dn is empty, D is not Fredholm. And the second problem is more technical at this point, but it's important that even if Fredholm, even if this Fredholm, this is not trace class. The trace operator will not be trace class. You cannot use all these methods. And in particular, you cannot define the it invariant. So how to deal with those problems? So I would say that with the first one, let me first discuss the first one. And dealing with the first one is basically by cheating. Namely, well, it's not always Fredholm. Let's consider operators for which it is Fredholm. And that's classically known as Calais index theorem. So here we consider operator D and add to it a potential. So I write I here because phi is self-adjoint, not very important at the moment. So you add a potential, let's call it d phi. So if I take this d phi squared, then I will get d squared plus I, let me better write, sorry, let me write this. Then it will be this. D is self-adjoint, D is the full operator with D plus and D minus. Plus I commutator D and phi plus phi squared. And phi is just potential. So think about some function. And now, in general, how does it look like? This is the operator of second order. Just think about Laplacian. This is in general operator of the first order. This is operator of the 0 order, just multiplication by a matrix. Now, we assume first that this commutator is 0 order. So no differentiations. What it means that it's a bundle map. That means that for experts that the leading symbol of D can be used with phi. So then all these things become just a potential. So you have a Laplacian, it becomes sort of shared operator, Laplacian plus potential. And this potential will be, so let me call it V of x. So at each point x of our manifold, we have a matrix basically. So we have matrix valued function. And the second assumption is, so let me draw this manifold. So we have non-compact manifold now. And this Calais index, sorry, I didn't say it, but that's the case the boundary is empty. So we have this non-compact manifold, so that there exists a compact part of it. And the number r such that for all x not in K, V of x is bigger than r. So V of x is self-adjoint matrix. It makes sense to say that it's bigger than some constant. It's a positive matrix, bigger than constant, outside of the compact set. So here could be anything, but here it should be positive. So basically, again, if we forget about details, which probably not very important at the moment, so basically that means that I assume that this phi grows fast at infinity and grows faster than its derivatives. So here derivatives of phi. So phi grows fast at infinity, and then this part is bigger than that part. And so then just that's again exercise in function analysis or differential equations that in this situation the operator d phi will be Fredholm. Basically, Schrödinger operator with growing potential is Fredholm, which basically means that there is a trapping of eigenfunctions. That's, you know, if potential is growing, then electron can run away. So it's Fredholm operator, and now we can consider its index. And a theorem which was initiated by Calais, who considered just an example of it. Constantine Calais, I think, was a student of Arthur Jaffa. He considered an example on R2, and then many people generalized it, and probably best results are due to Angel and independently Wunke in beginning of 90s. And they showed that if dimension of M is odd, so I actually don't need this theorem, but I couldn't resist to mention it. If dimension of M is odd, then so you can consider this K and the boundary of it. We can arrange this K to have a smooth boundary. So there will be hypersurface which separate my manifold into compact part and non-compact part. And so just roughly that there exists a well sort of canonically defined operator on sigma. So there is just an algorithm of how out of D and phi I define an operator on sigma such that the index of D phi is equal to the index of D. So in other words, this index, which is apparently allegedly much more complicated, index on non-compact manifold, reduces computation of its index reduces to computation of the index on sigma, where you can use Atiyah-Patodi-Singer index theorem and so on and so forth. So when you have this nice behaving potential, the operator is Fredholm and its index is computable. So that's the main message. And so that's basically where we started. And now we want to extend it to manifolds with boundary. And I should mention that there was a paper of, so the first paper of Shi, my co-author, sort of, so I gave him this problem to consider a case when the manifold is non-compact, but the boundary is compact. And then Shi extended there are some surprises there, but the short paper was eventually there is a formula. So you basically reduce the computation to computation on compact manifolds. But there is the EP invariant, everything there. But now we want non-compact boundary. So what to do with non-compact boundary? So I probably will draw it like this, even though it's just half space, but sort of pretending that it's more complicated manifold. So we have non-compact boundary. And when we started to look at it, it turned out that nobody actually ever considered, at least we didn't find, any reference to boundary value problems in such a situation. And so we started, it took us a while to extend the boundary value problem theory, which is classical theory. There are books on it, and kind of there's Shapiro-Lopatinsky condition for local boundary value problems and so on. And we actually sort of had hard time extending it to non-compact boundary till we found a very, very nice paper of Christian Baer and Werner Baumann in 2012. What they did, they just completely repackaged all the boundary value problem theory. So I would say that there are no official new results there. They didn't prove new boundary value problems or something. They just completely repackage all this classical theory. It's a long paper, like 80 pages, but it kind of replaces all the previous books on boundary value problems, and it's unified as one of the nice things that it has unified approach between local boundary value problem and Atiyah-Patodi-Singer boundary value problem and all the other boundary value problem, and they have very nice proof of definitions first, and then prove what's the elliptic boundary value problem, which includes Atiyah-Patodi-Singer and Shapiro-Lopatinsky. So that's kind of probably more interesting to analysis, but if you need to study boundary value problems, or if you need your student to study boundary value problems, for compact boundaries, classical boundary value problem, I think that's the best source now. So all the old books, classical books, I think Baumann is better, at least to study. They have very conceptual and nice approach to it. So I wanted to advertise this paper. And so we took this and we basically extended it to this situation with non-compact boundary. It's kind of, some things were not trivial to do, but at the end we did it. So we extended the whole theory. In particular, we proved that Atiyah-Patodi-Singer index, Atiyah-Patodi-Singer boundary value problem still could be defined here and gives an elliptic boundary value problem. So the first result that DAPS is flexible. And then we sort of studied the property and showed different properties of it. For example, there is something which is called gluing property. That if you have a manifold, let me draw it for compact manifold, just easier to draw, but it remains true for non-compact. So if you have your manifold and you cut it into two pieces, then you, and it could be with boundary here. Then you cut it into pieces. Then you can put Atiyah-Patodi-Singer boundary conditions here, Atiyah-Patodi-Singer boundary conditions here. Well, I'm cheating a little bit. Here is something which is called dual Atiyah-Patodi-Singer boundary condition, but that's a very minor change. Then the APS index here is equal to the sum of APS indices. Now, let's consider the situation. Let me probably simplify this picture just by drawing it as a half space. But that's basically a general manifold with non-compact boundary. So I draw it, think about half space. So we have this, well, I have to be more accurate. So what I mean there is that D itself is Calais type operator with this potential. And I consider, so D is, maybe let me write it. Calais. So we consider Calais type operator, we consider APS boundary value problem for it, and then it works. And then in Scalia's, there is this compact set over here. And so what you would actually like to do, as in Scalia's theory, you would like to cut off the compact part and non-compact part. But the problem is that there is a boundary. So that cuts the boundary. And if you cut the boundary, then sort of the boundary, as opposed to just usual index, the boundary conditions, you cannot just vary them easily. Index is very, very sensitive to the boundary conditions. So you cannot cut the boundary. At least we don't know how to do it. So what you can do instead, you can consider something which is almost your compact set. And here there is a small kind of cylinder around it. And then you can use the gluing formula. But remember, here your potential is positive. So here index is equal to 0. So when you cut it into the two pieces, this non-compact part, this part, becomes 0. So just because the operator is positive. So it doesn't have kernel. So everything reduces to this part which is almost compact. We call it almost compact manifold. So what's this almost compact manifold? It's basically a compact manifold to which cylinder side reached. Or another way of thinking about it, that you have just a cylinder, you have some boundary, let me call it n, it's the boundary of m. You consider n times some interval. Well, it could be small interval, it doesn't really matter. Let me call. So that's just a cylinder. And then you deform this cylinder. So you have some permutation of the compact permutation of this cylinder. We call it either almost compact or essentially cylindrical. Essentially meaning that outside of a compact set it's just a cylinder. But it's a cylinder of this type. So it's non-compact manifold times an interval. So and you can, and what this picture shows, that computation of the index reduces to computation of the index on this almost compact manifold, which also could be thought of as sort of cobordism between two boundaries. So in other words, what you have now two manifolds. You have now two manifolds, n0 and n1, and we have cobordism between them. But of course, the non-compact world, everything is cobordant to everything unless you impose some conditions. And here are conditions that sort of they everywhere just a product except in a compact set. So you have this non-compact cobordism. And now is, so I almost erased it. Now for this manifolds, so here everything is of product type, here everything is of product type, so Atiyah-Singer integrand will vanish here. So you can define all these things. You can consider two index GAPS minus integral of Atiyah-Singer. Well, the kernel you have to be a little bit accurate because now you have two kernels. So here you have iterator A0 and here you have iterator A1, and you have sort of cobordism between them. And here will be kernel of A0 plus kernel of A1. And that's a new thing. And the theorem is that this thing depends only on the boundary, so it depends only on those two boundary operators. So that's the theorem that this depends only on the boundary, and this thing we call relative at invariant. So this relative eta invariant is like eta invariant of this minus eta invariant of that. So morally, so the negative sign, I don't think, I don't have time to explain it, but it's basically because orientation of the boundaries are different. So basically this, but those two are not defined. But there are differences. And so we proved many theorems about behavior of this relative eta invariant, which shows that it behaves like it were the difference. So, for example, it's antisymmetric. That's relatively easy. There's something which we call cocycle condition. If you have 3 of them, then this is equal to eta A2, A0. So what do you expect? And the third thing I will not formulate, but because I don't have time, but basically for usual eta invariant, the deformation of eta invariant is computed using something which is called spectral flow. I won't explain it, but deformation is given by spectral flow. What it means is that if I deform one of those operators, then the spectral flow of it appears in the final formula in the same way as it would appear if it was a difference. And well, there are other properties of it, but now let me finish just in the last minute with what is missing. Remember, I told you that Atiyah-Patodi-Singer had this theorem, which is the first part of the theorem, that eta invariant is an invariant, and second is computation using spectral theory, using spectrum of A or hit kernel of A. So what is missing is hit kernel. Spectral is a little bit even harder, would be even better, but hit kernel formula. In other words, we need to make hit kernel great again. So the problem is, as I told you, that this hit kernel so let me just write this. This hit kernel is not, or here it's on the boundary, so I have to write A. Let me just write A squared. So this hit kernel is not trace class in general. So you can consider situations when it is trace class. If potential grows fast enough, geometry is nice, and so there are examples when it's trace class. Then everything works. Then just well, it's trace class that has a symptotic expansion. Then you could do this thing. But interesting situation is when it's not trace class. Now, but we have 2 operators, one like this, and we need to consider difference. And it's known a lot of situations when those 2 are not trace class, but they're difference. You know, hit kernel is almost local. So if you consider this difference of 2 operators, which are almost the same at infinity, then it's not surprising that the difference might be local, well defined. So it's kind of typical situation that this would be trace class. So you can try to use this for the formula for the eta invariant. And that's what we're trying to do. And now, sort of, well, let's say 90% theorem. Well, you see, it's only 90% theorem. It's not very ambitious. So if M is Rn plus, so half space. Oh, just let me say N is Rn. Just the boundary. This boundary M is just Rn. And the operators are of the form, this operator A is of the form, well, let me write what is A squared is. It's just the Laplacian plus log of x. So then the hit kernel is not of trace class. And that will be, say, A0, and A1 will be Laplacian plus log of x plus v of x, where v of x is a compact variation. It has compact support. So then, this, well, what's true that this difference, that's even not us, that this difference is trace class, it has a symptotic expansion. And then 90% theorem that in this situation, the relative eta invariant will be given by this hit kernel formula exactly like it was in difference. So there is some hope. I mean, this new invariant, hopefully, even in a much more general situation, is given by the same type of formula. So thank you.
you were saying that the index does not depend on the potential, or what?
It does depend on the potential, but in sort of mild way. So what you need to have is, so you have this manifold like this, and you have the potential. So first of all, your k depends on the potential. So where this potential is positive, where this combined potential, this I d phi plus phi squared is positive, this part is depends on the potential. And then we also define this operator on the boundary, which also depends on the potential here. But otherwise it doesn't, well, which is kind of expected because index is very stable. So if you start deforming this potential here, preserving this property that is positive, then the index will not change. So it could grow fast, it could grow slow, it doesn't matter.
En español, perdón, en dimensión 2 y 3.
Unfortunately, I couldn't.
En dimensión 2 y 3, aparte de la característica de Euler, ¿qué otros invariantes topológicos puedo recuperar como índices de operadores?
In dimensions размерности 2 и 3, какие топологические инварианты характеристики можно представить как индекс операторов?
In dimension 2, I don't know much. In dimension 3, well, there is, if you want geometric characteristics, then of course signature would be trivial, and then I really don't know a good example. So if you go to dimension 4, there are lots of them, because there are sort of Delbo operator. Actually, in dimension 2, there is just Euler characteristic, which is the index of the RAM operator, and there is also index of Delbo operator, which is sort of Riemann-Roch number. So that, and there is signature, which is the same as, oh no, in dimension 4 it's 0. But with bundle it's not 0, so if you have bundles, it might be not 0, so signature. But in general, you consider any geometric complex, like if you can consider the RAM complex, you can consider on the RAM complex the standard gradient, you get Euler characteristic, you can consider the signature gradient, and then you get signature operator, you can consider Delbo operator, you can consider, you will get holomorphic Euler characteristic, you can consider spin-Sidereck operator, then you get spin-C index. So in dimension 3, you can consider spin-Sidereck operators.
More questions?
With these differences, they belong to some important group?
No, that's difference of numbers. It invariant is a number. It's just numbers.
So there is no k-theoretic interpretation?
Well, that's, if you go to families, you will have it, but it's much harder. So we didn't do it. So at this moment, there is no k-theory, because it invariant is just a number. Index is just a number. So if you want to go to k-theory, to meaningful k-theoretical results, you need to go to family index. And family index with boundary is very difficult thing. So Paul's co-author knows it very well. But you can do it. But in this situation, we didn't even try.
More questions? No questions? Many thanks.